In this lecture we're going to begin our discussion on relative motion, and we're going to start that off actually with relative position. So here's a graph maybe of a classroom, and there are students within that classroom, and I've labeled the students and their positions on an XY coordinate system. And the origin can be any place in the room, it doesn't really matter, but we've set it in the center of this room. And so when I talk about the position of a student, recall that we labeled position with an R, and it's a vector, so we put the vector symbol over the top. But now we're going to add subscripts, and these subscripts are super important when it comes to relative motion, relative position. So as an example, let's think about the position of Kyle. So the position of Kyle I'm going to label with a subscript of K, but I'm also going to put a /O for the origin. And so the position of Kyle is equal to 5I plus 3J, and that would be in meters. Notice the X and the Y coordinate systems here are measured in meters, and Kyle is at 1, 2, 3, 4, 5 to the right, 1, 2, 3 up in the XY or Cartesian coordinate system. In a similar manner, the position of Tanya, also with respect to the origin, and that is a vector, is equal to minus 2I plus 3J. The position of Ed with respect to that origin is equal to minus 6I minus 4J. And again, all that's in meters. The position of Rachel with respect to the origin is equal to 3I minus 3J. And finally, the position of Sam with respect to the origin is 4I minus 9J. And again, all of those are in meters. But what if I'm interested in the position of one student with respect to the other? And so if I pick on Tanya and I ask Tanya, where is Kyle? She's going to tell you that Kyle is to the right. More specifically, 1, 2, 3, 4, 5, 6, 7 meters to the right. So I could write the position of Kyle with respect to Tanya is equal to 7I meters. In a similar fashion, if I asked Kyle, where is Tanya? Kyle would say that Tanya is 7 meters to the left. And so the position of Tanya with respect to Kyle, that is to say the position of Tanya as Kyle sees it, would equal negative 7I meters. So notice when I look at the position of Kyle with respect to Tanya and the position of Tanya with respect to Kyle, they're exact negatives of each other. And that makes sense. If I see you to the right, you're going to see me to the left. So it all works out the way you would think it would. So we just put minus signs in front of the I and J coordinates. Of course, if it's already negative, then minus a minus becomes a plus. Also notice the subscripts. The position of Kyle with respect to Tanya is a K over T, and the position of Tanya with respect to Kyle is a T over K. So whenever you reverse subscripts, you're going to reverse the sign, S-I-G-N, sign, of the coordinate. And that'll hold true also for the acceleration and the position, any derivative. You're also going to reverse the signs when you reverse the subscripts. Let's examine for a minute the position of Tanya with respect to Ed. Now as Ed views it, Tanya is forward and to the right. And if I count 1, 2, 3, 4, it's 4 to the right, 1, 2, 3, 4, 5, 6, 7 up, or 7 forward. So the position of Tanya with respect to Ed is 4I plus 7J, and that's in meters. We don't want to forget our units. But what might be the relationship between the position of Tanya with respect to Ed and the position of Tanya with respect to the origin and the position of Ed with respect to the origin? I could draw it out this way, and drawing it out might be more demonstrative than the math. Let's do the drawing first. So the position of Ed with respect to the origin is minus 6I minus 4J. We've already got that. And then there's the position of Tanya with respect to Ed, and I've drawn that already as well. Now if I add those two vectors together, the sum of those two vectors is right there. And that's the position of Tanya with respect to the origin. So here's the position of Ed with respect to the origin, and here's the position of Tanya with respect to Ed. And I've drawn them out, and notice what I've got here. I have the position of Ed with respect to the origin plus the position of Tanya with respect to Ed equals the position of Tanya with respect to the origin. Let's take a look at that more closely. Position of Ed with respect to the origin plus the position of Tanya with respect to Ed equals the position of Tanya with respect to the origin. That's what we just wrote. Now recall the position of Ed with respect to the origin is minus 6i minus 4j meters. And the position of Tanya with respect to Ed was 4i plus 7j meters. And you may recall when we add vectors, I'm going to add minus 6i plus 4i, there's the I components, plus minus 4j plus 7j, there's the j components, and this will leave me with minus 2i plus 3j, and that's all in meters. But notice minus 2i plus 3j is the position of Tanya with respect to the origin. So that all works out exactly the way we would anticipate. One other thing I'd like you to take note of is the subscripts. Ed with respect to the origin, Tanya with respect to Ed. If we were to multiply these, I know we're adding vectors, but when you add vectors, multiply the subscripts. And you'll notice the Eds cancel, and all I'm left with is Tanya with respect to the origin. So when you multiply subscripts, that's the same as adding the vectors together. The subscripts will cancel in the proper order. So keep that in mind. Also, do not forget that the position of Tanya with respect to Ed is negative the position of Ed with respect to Tanya. So I could rewrite this top equation as the position of Ed with respect to the origin equals the position of Tanya with respect to the origin minus the position of Tanya with respect to Ed. Right? I'm just bringing this vector to the other side. But that's the same as the position of Tanya with respect to the origin plus the position of Ed with respect to Tanya. And again, Tanya over origin times Ed over Tanya. The Tanyas cancel, and I get Ed with respect to the origin, which is exactly what I have there. So when adding vectors together, multiply their subscripts to see what cancels out. So let's take a look at one-dimensional motion. Let's pretend that we have a walkway at an airport. So imagine, if you will, that the velocity of the walkway with respect to the floor is equal to 1 meter per second. And that's going to be in the I-hat direction, so we're going to make it to the right. It is a vector quantity. Granted, it's all one-dimensional, but it's still a vector, so positive is to the right, negative is to the left. Now further assume that a person can walk with a speed of 1.5 meters per second. And for now, we'll have that be to the right. So if they're walking at a speed of 1.5 meters per second and they're on the walkway, then that velocity would be with respect to the walkway. So somebody on the floor would see the person moving at the velocity of the walkway with respect to the floor plus the velocity of the person with respect to the walkway. And so the person on the floor would see that other person who's walking moving at 2.5 meters per second to the right. So you simply add the speed of the person on the walkway plus the speed of the walkway itself. Notice the subscripts. Walkway with respect to floor, person with respect to walkway. The walkways cancel, and this would be the velocity of the person with respect to the floor. Now as a kid, we used to love to go backwards on those walkways. So in that scenario, the velocity of the person with respect to the walkway would equal minus 1.5 meters per second. So the walkway's moving to the right and you're moving to the left trying to fight the traffic. The velocity of the person with respect to the floor would still equal the velocity of the walkway with respect to the floor, plus the velocity of the person with respect to the walkway. But in this scenario, it's 1 meter per second in the I, plus a negative 1.5 meters per second in the I, and so the result is a negative 0.5 meters per second in the I direction. I'm moving backward in that scenario. And if I walk at exactly 1 meter per second, I don't go anywhere because I would end up with 0. So even though my legs are moving, I'm not traveling along the floor. Well, these are vector quantities, and so oftentimes we're going to be moving in 2 dimensions, sometimes even 3, but very often in 2 dimensions. Some real good examples of that are airplanes traveling through the air. Keep in mind there's a wind, and so in this scenario you have the velocity of the plane with respect to the air. You also have the velocity of the air with respect to the ground. This is generally the wind speed, or the air speed. And so, and in the end, you'll have the velocity of the plane with respect to the ground. Looking at your subscripts, you can see in this case the a's will cancel. So I add these velocities together and I get this last velocity. Keep in mind, those are vector quantities, generally in 2 dimensions. Same thing would hold true for a boat traveling in a moving body of water. You'd have the velocity of the boat with respect to the water. You'd have the velocity of the water with respect to the shore. If I add these together, you can see the w's will cancel. I'm left with the boat with respect to the shore. So I have the velocity of the boat with respect to the shore. And again, these are vector quantities. Let's take a look at an example. So here I have an airplane, and I'm flying with a compass heading of 30 degrees east of north. Now we got to be careful about this. So here's north, and here is east. So east corresponds to my x-axis, north corresponds to my y-axis, positive x, positive y. So 30 degrees east of north would be in this direction. So there's my 30 degrees, and that's the compass heading of my airplane. So that would be the velocity of the plane with respect to the air. And I'm moving at a speed of 175 meters per second. So my speed, notice there's no vector sign there, my speed is 175 meters per second. That's the speed of the plane with respect to the air. Now the wind is blowing out of the west at 10 meters per second. So it's blowing in this direction. So this is the velocity of the air with respect to the ground. And that's going to be 10 meters per second. And it's coming out of the west, meaning it's blowing to the east. So this would be in the I hat direction. So the velocity of the plane with respect to the air, vector quantity, is 175 meters per second. I'm going to do this in polar form at an angle of 60 degrees, not 30 degrees. Because remember, in polar form, you always measure with respect to the positive x-axis. So if this is 30 degrees up here, this must be 60 degrees here. So my velocity is 175 meters per second at a positive 60 degrees. And I could write that then as 175 meters per second, cosine of 60 degrees, right? The adjacent side is in the x direction, so there's my I hat, plus 175 meters per second, sine 60 degrees, and that's j hat. Here's the sine, that's the opposite side of 60 degrees. So what direction am I traveling? So the velocity of the plane with respect to the air plus the velocity of the air with respect to the ground is going to give me the velocity of the plane with respect to the ground. Well, the velocity of the plane with respect to the air is 175 meters per second cosine theta, and that's going to be 87.5 meters per second I plus 175 meters per second sine 60 degrees. That's going to be 152 meters per second j. That's the velocity of the plane with respect to the air, plus 10 meters per second in the I hat direction. And so 87.5 plus 10, those are my I hat components. That's going to be 97.5 meters per second in the I, plus 152 meters per second in the j. And if I wrote that in polar form, that would be 180 meters per second at an angle of 57.2 degrees. Now keep in mind, that's with respect to the east. So 57.2 degrees, I would say 57.2 degrees north of east, but in general we always use something less than 45 degrees. So that would be 32.8 degrees east of north. And that would be my direction. And this would be my speed. Okay, so 180 meters per second is my speed. Now in part B, what if I want to travel due north? What direction do I need to point the plane? So a diagram here is super important. So I want to travel straight to the north. So this would be the velocity of the plane with respect to the ground. So that means, keeping in mind that my wind is blowing in this direction, so that's the velocity of the air with respect to the ground, and that's 10 meters per second. Clearly I'm going to have to point my plane in this direction. So this is the velocity of the plane with respect to the air. And so you can see that the velocity of the plane with respect to the air plus the velocity of the air with respect to the ground, those two vectors here and here, are going to equal the velocity of the plane with respect to the ground. Well, I know the magnitude of this side is 175 meters per second. And I know the magnitude of this side is 10 meters per second. And so I can find this angle by knowing that the sine of theta is equal to 10 meters per second divided by 175 meters per second. Notice the units cancel, which they need to. So that tells me then that theta is equal to the arc sine of 10 over 175. No units because they canceled out. And that's going to be 3.28 degrees. So I have to fly at 3.28 degrees west of north. And if I actually did this with respect to the positive x-axis, then theta is equal to 93.28 degrees. And if I wanted to know my speed, I would take 175 meters per second at an angle of 93.28 degrees plus 10 meters per second at an angle of 0 degrees, because it's due east, and that's at 0 degrees. If I add those together, I get 174.7 meters per second at an angle of 90 degrees, which is what I want because it needs to go due north. And you could break this down. I could do 175 meters per second cosine 93.28 degrees in the I plus 175 meters per second sine 93.28 degrees in the J plus 10 meters per second, that's the airspeed in the I. Now this, if I did that right, should be negative 10 meters per second. And so this is all I'm left with, and that would be 175 meters per second, 174.7 meters per second.